Greetings to dear friends, thank you for choosing the BigDark channel for teaching scientific content. Please do not forget to subscribe, like. Radar, radio detection and ranging, is a detection system that uses radio waves to determine the distance, range, angle, or velocity of objects. It can be used to detect aircraft, ships, spacecraft, guided missiles, motor vehicles, weather formations, and terrain. A radar system consists of a transmitter producing electromagnetic waves in the radio or microwaves domain, a transmitting antenna, a receiving antenna, often the same antenna is used for transmitting and receiving, and a receiver and processor to determine properties of the object. Radio waves, pulsed or continuous, from the transmitter reflect off the object and return to the receiver, giving information about the object's location and speed. Radar was developed secretly for military use by several nations in the period before and during World War II. A key development was the cavity magnetron in the United Kingdom, which allowed the creation of relatively small systems with sub-meter resolution. The term radar was coined in 1940 by the United States Navy as an acronym for radio detection and ranging. The term radar has since entered English and other languages as a common noun, losing all capitalization. During RAF radar courses in 1954/5 at Yatesbury Training Camp, radio azimuth direction and ranging was suggested. Citation needed. The modern uses of radar are highly diverse, including air and terrestrial traffic control, radar astronomy, air defense systems, antimissile systems, marine radars to locate landmarks and other ships, aircraft anti-collision systems, ocean surveillance systems, outer space surveillance, and rendezvous systems, meteorological precipitation monitoring, altimetry and flight control systems, guided missile target locating systems, self-driving cars, and ground-penetrating radar for geological observations. High-tech radar systems are associated with digital signal processing, machine learning, and are capable of extracting useful information from very high noise levels. Other systems similar to radar make use of other parts of the electromagnetic spectrum. One example is LiDAR, which uses predominantly infrared light from lasers rather than radio waves. With the emergence of driverless vehicles, radar is expected to assist the automated platform to monitor its environment, thus preventing unwanted incidents. Applications. In aviation, aircraft can be equipped with radar devices that warn of aircraft or other obstacles in or approaching their path, display weather information, and give accurate altitude readings. The first commercial device fitted to aircraft was a 1938 Bell Lav unit on some United Airlines aircraft. Aircraft can land in fog at airports equipped with radar-assisted ground-controlled approach systems in which the plane's position is observed on precision approach radar screens by operators who thereby give radio landing instructions to the pilot, maintaining the aircraft on a defined approach path to the runway. Military fighter aircraft are usually fitted with air-to-air targeting radars, to detect and target enemy aircraft. In addition, larger specialized military aircraft carry powerful airborne radars to observe air traffic over a wide region and direct fighter aircraft towards targets. Marine radars are used to measure the bearing and distance of ships to prevent collision with other ships, to navigate, and to fix their position at sea when within range of shore or other fixed references such as islands, buoys, and lightships. In port or in harbor, vessel traffic service radar systems are used to monitor and regulate ship movements in busy waters. Meteorologists use radar to monitor precipitation and wind. It has become the primary tool for short-term weather forecasting and watching for severe weather such as thunderstorms, tornadoes, winter storms, precipitation types, etc. Geologists use specialized ground-penetrating radars to map the composition of Earth's crust. Police forces use radar guns to monitor vehicle speeds on the roads. Smaller radar systems are used to detect human movement. Examples are breathing pattern detection for sleep monitoring and hand and finger gesture detection for computer interaction. Automatic door opening, light activation, and intruder sensing are also common. Radar signal. A radar system has a transmitter that emits radio waves known as radar signals in predetermined directions. When these signals contact an object, they are usually reflected or scattered in many directions, although some of them will be absorbed and penetrate into the target. Radar signals are reflected especially well by materials of considerable electrical conductivity such as most metals, seawater, and wet ground. This makes the use of radar altimeters possible in certain cases. The radar signals that are reflected back towards the radar receiver are the desirable ones that make radar detection work. If the object is moving either toward or away from the transmitter, there will be a slight change in the frequency of the radio waves due to the Doppler effect. Radar receivers are usually, but not always, in the same location as the transmitter. The reflected radar signals captured by the receiving antenna are usually very weak. They can be strengthened by electronic amplifiers. More sophisticated methods of signal processing are also used in order to recover useful radar signals. The weak absorption of radio waves by the medium through which they pass is what enables radar sets to detect objects at relatively long ranges at which other electromagnetic wavelengths, such as visible light, infrared light, and ultraviolet light, are too strongly attenuated. Weather phenomena, such as fog, clouds, rain, falling snow, and sleet, that block visible light are usually transparent to radio waves. Certain radio frequencies that are absorbed or scattered by water vapor, raindrops, or atmospheric gases, especially oxygen, are avoided when designing radars, except when their detection is intended. Illumination. Radar relies on its own transmissions rather than light from the sun or the moon, or from electromagnetic waves emitted by the target objects themselves, such as infrared radiation, heat. This process of directing artificial radio waves towards objects is called illumination, although radio waves are invisible to the human eye as well as optical cameras. Reflection. If electromagnetic waves traveling through one material meet another material, having a different dielectric constant or diamagnetic constant from the first, the waves will reflect or scatter from the boundary between the materials. This means that a solid object in air or in a vacuum, or a significant change in atomic density between the object and what is surrounding it, will usually scatter radio waves from its surface. This is particularly true for electrically conductive materials such as metal and carbon fiber, making radar well suited to the detection of aircraft and ships. Radar absorbing material, containing resistive and sometimes magnetic substances, is used on military vehicles to reduce radar reflection. This is the radio equivalent of painting something a dark color so that it cannot be seen by the eye at night. Short radio waves reflect from curves and corners in a way similar to glint from a rounded piece of glass. The most reflective targets for short wavelengths have 90 degrees angles between the reflective surfaces. A corner reflector consists of 3 flat surfaces meeting like the inside corner of a box. The structure will reflect waves entering its opening directly back to the source. They are commonly used as radar reflectors to make otherwise difficult to detect objects easier to detect. Corner reflectors on boats, for example, make them more detectable to avoid a collision or during a rescue. For similar reasons, objects intended to avoid detection will not have inside corners or surfaces and edges perpendicular to likely detection directions, which leads to odd-looking stealth aircraft. These precautions do not completely eliminate reflection because of diffraction, especially at longer wavelengths. Half-wavelength long wires or strips of conducting material, such as chaff, are very reflective but do not direct the scattered energy back toward the source. The extent to which an object reflects or scatters radio waves is called its radar cross-section. Beam path and range. A radar beam follows a linear path in a vacuum but follows a somewhat curved path in the atmosphere due to variation in the refractive index of air, which is called the radar horizon. Even when the beam is emitted parallel to the ground, the beam rises above the ground as the curvature of the Earth sinks below the horizon. Furthermore, the signal is attenuated by the medium the beam crosses, and the beam disperses. The maximum range of conventional radar can be limited by a number of factors. Line of sight, which depends on the height above the ground. Without a direct line of sight, the path of the beam is blocked. The maximum non-ambiguous range, which is determined by the pulse repetition frequency. The maximum non-ambiguous range is the distance the pulse can travel to and return from before the next pulse is emitted. Radar sensitivity and the power of the return signal as computed in the radar equation. This component includes factors such as the environmental conditions and the size, or radar cross SE. Thank you for being with us until the end of the program. Be sure to mention your opinions about the educational video in the comments section.